Welcome to video number 2, where we will talk about testing, conducting tests in R in your R code. This video will have a kind of longer intro because it's, in my opinion, more important to understand the concept rather than now me teaching you some syntax or some exact code. And let's start with easy children's toy example. That it means we can understand the things better. Generally, I think many of you have played with these dominoes in the when you were younger, or maybe even now, and built these things where one goes off all the way down, the track goes off. And let's think of one of these things as our piece of code. We run a code, and based on that the rest of the code runs. And well, if we develop packages or if we write really elaborate code, this may look like this, like one of the longest of these domino tracks that we know. Okay, if we imagine our code like this domino track, there may be occasions where if a condition is not fulfilled here, so maybe at the beginning of our code, well, an error will happen somewhere downstream the code. And we want to prevent that, because code, especially if you create loops, can take for a long time, and if it fails, we want to know that as early as possible. I have had code with millions of rows in the data frame which took days to run, and I really need to know as early as possible if this code works or not. So yeah, we want to prevent all the domino track from going off. And maybe if you played with these dominoes, you have also did this, like every once in a while, maybe let's say every 20 dominoes, you just removed one. Or in my case, I don't know if other people did that, and I don't know why actually we did that, but we just put one, we laid one down, one domino. And we can think of testing in R as the one domino that we take out and lay down, because it prevents our code from just entirely running, taking a lot of time, and then running into an error finally. So this is one application of testing. We want to have a breakpoint at earlier stages of the code, preferably if compared to testing or running into the error at the very end. So that is one application. And the second application, again, actually I have to come back and I have to say, it is nice if our code outputs the error, but what's really bad if we don't get the error and our code runs with some mistake in it. So that's the second application of testing. Let's look at this example, and we can imagine our code now like a factory. We have an item, this purple triangle, and it goes through let's say this is maybe a data frame or whatever, some kind of object. It's moved through our factory and into this machine, which can be, for example, a function. And this machine is actually perfectly designed for purple triangles. It only can process purple triangles in a proper way. And then as an output we get this beautiful star. If, for example, we have a green hexagon as an item that's put into this machine, we get, did you see the difference? Like this is a 7-edged star and this is an 8-edged star. So we get a wrong product, but our machine doesn't fail. It doesn't break down. It still produces something, but it's wrong. It might be hard to see that this is wrong because we don't get an error message. So this is really problematic. We want to prevent this as hard as possible. And how do we want to prevent it? I've come up with another children's toy example. I mean, all of you know these. Either you had one yourself or maybe you saw it in a movie or whatever. Let's just implement this in our factory. And our factory is our code. So we want our item that's here in our machine or in our factory, we want to go through this thing as a test. If it passes the test, it can go into the machine. If it doesn't pass the test, can't go into the machine. So if the purple triangle is processed, goes through a machine, we are happy. If the hexagon passes the test or goes through the test, it doesn't pass, well, we are unhappy. But at least now we know we don't produce this wrong star. And the thing why we want to do automatic testing or testing with functions in R is because currently we are already testing. All of you are doing this. How are we doing it? Like an inspector. Actually, if we wouldn't have this, we maybe here on the right there should be an inspector that looks at every star all the time if this is correct or not correct. Well, this is very, very tedious. If I would be working in this factory and I would have to compare the stars all the time, this is not really time effective and also not really scalable. Currently, what we are doing, if we transfer it back to R, we are testing in the console. So all of you, if you write functions, if you write code, you type little stuff in the console and you test if it works. You check out your data frames after you wrangled them. All of you do it. I do it as well. It's not a problem, but we should note it. We check out our data frames. Did this work? Well, this gets very difficult if you have millions of rows to check every row. We constantly run our Shiny app, whether our feature worked that we tried to implement, and so on and so on. So actually we are already testing a lot, but not in this kind of standardized and automated way. And therefore I want to introduce two concepts of testing in this video. The first is a package called TestStat. It's a widely used package for implementing tests in your R code. And then stop if not. This I included because it's a really simple base R function, no package needed. This is in default R included. TestStat is a very cool and big package and widely used. So we have, let's say, the most prominent and the most basic one. And then there are, of course, also many other options. But it's more important to understand this concept and that you have already heard of it, so you can already start experimenting or playing around with it. Cool. Let's start with the stop if not command. It's quite simple in its basic application. Well, the condition or the test that you are conducting, it can be really complex. But the basic stop if not function is just really simple. It's an easy base R function that stops the current code if a condition is not met. And the condition is what we specify in the stop if not function. So to explain the name and to go back to our factory example, we stop the machine if the processed item is not a triangle. So stop if not. Cool. I think it gets more understandable if we check out a quick example in R. Don't want to get too difficult of examples. We can check out some examples in the next practical, but let me zoom in a little bit for you guys. So what I created here is a little data frame, this DF data frame with the federal states of Germany and the respective population. See here. So we have Bavaria with the 30 million people. This is just for practicing reasons. You can ignore whether this is actually perfectly accurate or not. I don't know this. I created this data frame and then, okay, what did I do? I wrote a function. You all are familiar with functions. The function is called max population and it should spit out the maximum population of a data frame. So the function requires a data frame. Then what does it do? It creates an object called maxPop, maximum population, which is the maximum of our population column. You see this column here. And before that, we have the stop if not command. So the code stops if the number of rows of the data frame is not 16. I added this as a security check, as a test, because I know that Germany has 16 federal states. If we have more or less than 16 rows, I can for sure know that something is wrong. So our code should stop if we have not 16 rows. If we have 15 rows, 17 rows, I know that something must be wrong. So I implemented this in our in my function. Then I can load the maximum population function to my environment. I already did this. And I can run the function on my data frame here, line 21. And as an output, we see we get the maximum of 17.99 million, which is perfectly fine. This is correct. This is the population of Nordrhein-Westfalen. And To see what it does, we could imagine Germany having 15 federal states. Now I would change the condition to stop if not the number of rows is 15. Let's try to run it. Okay, now we get an error. This is actually good. We want an error if things go wrong. So that's why we implement this testing. We get an error in maximum population of the data frame because the number of rows of the data frame equals 15 is not true. This is not true because we have 16 rows. So actually this worked, and this is a really simple example how this stop if not command works. I think every once in a while it makes sense, and especially for things that really must not go wrong, to implement some kind of test with stop if not, or of course other functions that do virtually the same. Okay, so far for stop if not. This was quite simple example. Let's move on to test that. Test that is not one single function, it is a package. You can see the icon here, and it is a package that implements even more systematic, large-scale and complex testing. So it actually it just has more capabilities than this single function of stop if not. You have a lot of things you can do with the package, but it is still quite understandable in my opinion, because, or upon multiple reasons, because this is conducted in a separate R file. So you have your tests in a separate file with stop if not. You have it in your in the file where you are also running your analysis, for example. You can conduct your tests in a separate file with this test.dat package. And since it takes a little bit of setup, this is because also there the longest code lines are written. I think this is mainly used for package development, but I have to say it can also be useful for very long and complex code that you guys might write in the future or are already writing. I don't know this. And also I recently saw that there is an expansion for Shiny apps, which all of you guys know how to create. So I think test.dat can be a powerful and really helpful tool in preventing us from making big errors. Just some screenshots. In the next practical we will look at test.dat in a little more detail. So here, let's see, we would have two R files. On the left side, this minmax.r. We will look at this very example in the next practical. We will write our function, do all our stuff, and then we have automatically created our test minmax.r file where we can create our tests. Here we test that with the function test.dat. We test that, and then you give a name, you give your test a name. That minmax, which is a function we will write on next Friday, returns a vector of the length 2, which is important. And then there are a bunch of functions on what we expect from our function. Here we expect the length of running the minmax function on this array from 1 to 10 to be 2, because if this is a function that puts out the minimum and the maximum of an array of numbers. If we print the minimum and the maximum, these are two things, so we want a vector of the length 2. So this is a separate test, and then the testing is actually conducted. If you do package development and you run the DevTools, here you have, as always, you have your environment, history, and so on, but you also get this build tab. And your tests will all be run in this tab and then put out in a summarized way. So here we are only doing one test, but it's summarizing all of our tests. It can fail, it can return a warning, it can return a skip, and also pass. So pass is what we want. Here we run one test, and testing returns an OK or a pass. This is the same. So all tests have succeeded, and this means our code can run, our functions work. If it somehow fails, for example here, the minmax function was just edited in a wrong way, and then we get a vector of the length 3, well, then this test fails and we get notified that this failed. And it's really important for us to notice. So then we see the test fails, we should go back to our code, try to solve this. So these were just some just a little sneak peek to what we will look into in the next practical in this package test that that helps us to detect and flag errors in our code. As a conclusion, I think this has actually a lot of similarities to the previous video on renv, because to you it might seem unnecessary now, I don't know, but it will be inevitable and very, very time saving in the future. And I think many people would agree with me that some people that write code need to learn this the hard way, so they won't start testing now and doing the dependency management for renv as well until they fail once really, really hard. But I don't want you to run into this mistake, so that's why we talk about package dependency and also testing in these two videos. Just imagine as like what could go wrong, that you realize that you published some wrong code or even results based on wrong code. You published this in a journal article or newspaper article, and you realize it afterwards because the R code actually worked, but it was wrong. Well, that would be really, really embarrassing and bad for you. So yeah, that's why we think that these two helpers are very important. And with that, I will see you in the third video.